Alright, so now we are going to go over our runtime analysis of Bubblesort. Now, the question is, how long does it take for Bubblesort to work? Right? We've pointed out this is the example of a polynomial a quadratic time algorithm. So let's show what we mean by that. Alright, so worst case scenario for Bubblesort is that we pass in an array that basically is completely reversed. Right? Completely reversed array. Okay? So the next step, so at the beginning of the first step, at the first run, what happens? 5 swaps with 4, 5 swaps with 3, then 5 swaps with 2, then 5 swaps with 1, right? That's the way that Bubblesort works. This pair, then this moves up here, then this pair, then this pair, then this pair. And we're left with this. 4, 3, 2, 1, 5. Right? Not looking quite sorted right yet. Okay, then we run Bubblesort again. We compare 4 to 3, so then they swap. We compare 4 to 2, and they swap. 4 to 1, and they swap. And 4 to 5, and they stay still. So we end up with 3, 2, 1, 4, 5. Right? And then we do that again with 3, and so on and so forth. So then we get 2, 1, 3, 4, 5, and then we do another comparison and we get 1, 2, 3, 4, and then 5, right? All right, and then after that, I said, okay, so we've moved, and so we've done 4 runs, and there were 5 items, so we can stop after 4 runs because we got 5 up there, then 4, then 3, then 2 into place, and the last item we kind of get into place. It just falls into place for free, right? If these n-1 items are in place, then the nth item has to be in place by default, right? There's nowhere else to go for it to go but for one option. All right. So the question is, how many comparisons did we do for each of these, right? In between each of these steps, how many comparisons did we do? Well, we compared 1, 2, 3, 4 pairs, and then we compared 4 pairs, and then we compared 4 pairs over here, then we compared 4 pairs. So we did 4 comparisons over here, 4 comparisons over here, 4 comparisons over here, and then 4 comparisons over here to get what we did. How many pairs did we compare? We compared 4 pairs, right? There were 4 pairs. Each run there are 4 pairs, right? 1 pair, 2 pair, 3 pairs, 4 pairs. Right? Because if you've got in a list, there are of n items, there are n-1 adjacent pairs. Right? So if there were let's go over here and say we had 1, 2, 3, 4, ... right? And we went all the way up to 99 and 100, right? These are our pairs, right? These are our numbers. How many pairs, adjacent pairs of numbers are there? Well, there's this pair over here, there's this pair over here, and then there's this pair, and so on and so forth, right? There are 99 adjacent pairs, right? We have 100 numbers, there are 99 adjacent pairs. Similarly, if we have 1, 2, 3, ... all the way up to n-1, if we have n items, right, then how many pairs are there, right? We have n-1 adjacent pairs. Of course, my drawing on this is terrible because I've never been good with that, with a mouse like this. All right, so n-1 adjacent pairs. Okay. So and then we need n- runs to do this. All right. So let's take a look at this. So we run this outer loop n-1 times. We run this inner loop n-1 times. Right? So we do n-1 comparisons. So all told, how long does this take? Well, this takes n-1 outer loop, right? Outer loop runs. And each of those outer loops takes n-1 runs n-1 times, right? We look at n-1 pairs. So that's equal to n squared. Let's see. So that would be n squared minus what? That would be minus, if you FOIL that out, that becomes minus 2n. So that's the amount of comparisons we have to do, right? So, and because the biggest term in here is n squared, we say this is a big O of n squared algorithm, right? So now we'll demonstrate this so there's a quadratic relationship between the number of items and the runtime this is going to take. So let's take a look, right? We ran this once. We have 1,000 items in our list. We're going to sort the list. Run it. Boom. It takes 104. Sorry, it takes 104 milliseconds. Let's go ahead and multiply that by 10. Right, and it's not going to take 10 times longer. It's actually going to take substantially longer. It went from 1,000 to 300. All right, and what happens here now when we bring it up to 100,000? Right, it doesn't take very long to build a list. But as we're going to see, this is going to run for a while. It will run for a good amount of time. It will get done though. And the reason is because by increasing it by 10, we're not multiplying the amount of work we have to do by 10. We're increasing it closer to on the order of increasing the amount of work we have to do by about, 100 times. And the reason for this is that when we add another item to sort, we essentially add another layer, right? If we were to add another item over here, right, we would have to add in if we were to add in 0, for instance, over here, we would have a 0 here, a 0 here, a 0 here, a 0 here, and then finally we'd have to do one more layer of sorting, and each of these so we'd do 5 runs over 5 pairs. Adding another item would make us do 6 runs of 6 pairs, right? And adding another item would do 7 runs of 7 pairs. So not only are you adding in more work for that, just from adding that item, but each of the previous runs that you would have to do, right? Each of the other numbers now has more work to get sorted, right? This is still running. So it takes a substantially long time. So, now, as I mentioned, this is an unoptimized version of Bubblesort, okay? And again, you might be wondering, okay, why am I calling this an O of n squared when there's this minus 2n in here? And the answer is that as these numbers get big, this n gets really big, it gets utterly dwarfed by, as these numbers get really big, the n square utterly dwarfs the 2n. The 2n just doesn't matter in the long run, right? Right? Suppose we're sorting 1,000,000 items, right? Well, then the runtime becomes equal to 1,000,000, so that's 10 to the 6th, right? And when we square it, it becomes 10 to the 6th squared, which is 10 to the 12th, minus, 2 times 10 to the 6th plus 1. So now let's go. So when we do our big O analysis, right, what happens? Well, let's note that basically that this plus 1 or minus 1, plus 1 or even with minus 1 or even with like plus 10 or something, this constant factor just does not matter, right? It gets utterly eclipsed by this thing over here, right? By this 2n term, right? Utterly eclipsed by it. On the other hand, this 10 to the 12th utterly eclipses the 10 to the 6th. That means there's 6 more zeros, right? Right? This is 1,000,000. So 1 followed by 6 zeros. And this is 12,000,000. Sorry, and this is 10 to this. Sorry, and this is 10 to the 12th. It is an utterly monstrous term in comparison. Right? And it only gets worse even if it becomes like 10 million. Right? If it becomes 10 million, then if n becomes 10 million, then this term becomes this. But this term becomes this. And the difference between, and the, not even the difference is kind of the wrong term, even though it expresses what I'm trying to say. Like, obviously the distance grows, but just the gulf between the difference just grows as we add this up. So when we do a big O analysis, we do two things. The first is that we, as you'll see in your homework, we toss out all the lower terms, right? If we have an n squared, we'll just toss out the O of, if we have an n squared, we'll toss out the n terms and the constant terms just to make things simpler, because as we get to very monstrous sizes, they don't even matter, right? And look at that. So from going from about 2,000 milliseconds to about 2,600 milliseconds, right? I like that. That kind of proved what I was trying to say. Awesome. So this took a monstrously long time. All right. Let's go ahead, and I think actually it's not liking the fact that there are just so many items in my terminal that I had to print out. That might have actually also impacted. That took a very long time, indeed, to run. All right. And part of the problem might have been just printing all of them out. All right. So these quadratic runtimes, they get very, very dangerous very quickly, like in terms of the amount of space. But you can still sort a substantial amount of items. We were sorting 100,000 items fairly quickly. And there are better sorting algorithms.